All right, awesome. Sorry, just go check the time. Okay, this is odd. I've never done this before, but I'm Jim Plank, and I'm giving a talk to two people that's getting recorded. This is a talk on erasure codes, erasure-coded storage systems. The problem space, the erasure codes these days are everywhere. Every storage system that you can imagine that has multiple components or a network component is going to have erasure codes. And the reason is because when you have multiple components or networking, then things are going to fail. Individual components are going to fail. And the way we handle failures is through redundancy, so that you add extra redundancy of your data onto your storage system so that when components fail, you can actually read the data back. And the technology for that is called erasure codes. Now, what I'm going to talk about today is I'm going to summarize the current state of the art with regard to erasure codes from my perspective. And then I'm going to outline two projects that I've been leading recently. One is going to be work on minimizing I/O when you recover, when you have failures in a storage system. And the second one is completely different. I call it screaming fast Galois field arithmetic. It's really a game changer in the world of erasure codes on using special coprocessing instructions to do Galois field arithmetic, which lies at the heart of most erasure codes, really fast. And I'll talk about why that's a game changer. Okay, so let's get started. First off, you got some data, and you got some storage nodes, and you want to be able to store the data on the storage nodes in such a way that when something breaks, you can get your data back. That's the base problem of using an erasure code. Now, to get more concrete, we say usually you take your data and you're going to store it on some number of disks, and we always call that K. So you have K disks worth of data, and you have N total disks that you're going to store your data on, and being greater than K. And the erasure code is the technique that shows you how to store that K disks worth of data on N total disks so that you can get the data back when things fail. Now I'm going to go through some nomenclature just so that everyone's on the same page. So first piece of nomenclature, an erasure code is systematic if the data that you store on your disks actually includes the data in the clear. So the actual data is on your storage. Obviously this is good for speed, because in the common case when things aren't failed, you can actually grab your data and not have to decode it. However, some systems might not want to have that. Typically in these systems, we'll say that there are K disks worth of data, M disks worth of coding, K plus M equals N, and sometimes we call the coding disk parity disks. On the flip side, a non-systematic erasure code doesn't store the data in the clear. So what's being stored on disk doesn't include the data, and every time you want to read data, you have to do a decoding operation. When disks fail, the failure mode is called an erasure. And that means that when your storage fails, you know that it's failed and you can't get the data back. And that's as opposed to an error, which happens in communication systems when your data gets corrupted, but you don't know it. With storage, your data is gone, and that's called an erasure. There's a buzzword for erasure codes called MDS, standing for maximum distance separable, which I think is just a horrible, horrible term because it doesn't convey any intuition. But an MDS code means that you can tolerate any M failures. And it doesn't matter which disks fail, as long as M or fewer of them fail, an MDS code will allow you to read your data back. And that's as good as you can do from an information theoretic standpoint. It's taken me a couple years to come up with these next couple slides because I've had to figure it out. When you talk about storage systems, often you talk about a stripe. And a stripe has two views, and there are two ways that you talk about a stripe. There's a theoretical way, and then there's a systems way. Now, let me talk about the theoretical way. The theoretical view of a stripe is going to be a collection of W-bit symbols that's going to be held on disk, and it's the minimum collection of these symbols, and so it reduces your storage problem to really a math problem where you have a certain number of variables that you're storing on disk, and then if a disk fails, you're going to lose all those variables. And the two extra pieces of variables we add here is each of these symbols is W bits long. Sometimes W is 1, so it's just a bit. and each disk is holding R of them, and R stands for rows. So each disk, so you can view your stripe, your theoretical stripe, as a rectangular matrix where the columns represent disks and then the rows represent symbols that are going to be held on disk. Now when you try to realize this on a storage system, that's not how you do it. Instead, with the storage system, you have a different definition of a stripe. Basically, it blows up the theoretical definition so that instead of having W-bit symbols, you have blocks, which are sometimes sectors or sometimes bigger entities, and each block is partitioned into symbols, and then the little theoretical stripe is one little partition of that system. So I draw in this, if you can read the picture, the little yellow boxes represent the individual symbols that are part of your stripe, but you're going to group a whole lot of those together to make one big stripe. Now, why are there two views? Well, the first is because W is often a very small number, sometimes 1, which is 1 bit. And if you could think, and often the operation that you do on the bit is exclusive OR. Well, it's a lot more efficient to do exclusive OR on 64-bit or 128-bit or even pages, because it's a lot faster to do it that way. And that's why we have the systems view, which coalesces all these bits onto bigger blocks. The other reason is that typically what a storage system will do is it'll take each disk and it'll break it up into stripes, and then it will rotate the identities of the disks within the stripe so that you can alleviate hotspots. Because often when you're writing to a single block, you might be writing to multiple coding blocks, and that puts an asymmetric load on there. Now, what I'll talk about for the most part is going to be the theoretical view of the stripe, although when I get into implementation, we talk more about the systems view. Okay, given that, I'm just going to go over the basics of erasure codes. A typical erasure code is represented by a generator matrix. And the generator matrix has K times R columns and N times R rows, and it's going to be multiple. The data itself is represented by a K times R vector, and this matrix vector product defines the coding. So for example, to calculate a coding word, you're going to do a dot product of one of the rows of the matrix on the data. And that's how we do encoding. Now, a systematic erasure code includes the data in there on the storage system, so the top of the generator matrix is an identity matrix so that you can see that the data is being held in your system. Now, when you decode, actually you like to use a non-systematic code to show decoding. If you have a couple failures, you'll note that the disks on which these fail will correspond to rows of the generator matrix. So you take the rows of the generator matrix that correspond to the failed disks and you delete them. Then you take this picture and turn it into a more mathematical picture, right? You have a matrix times the data equals the surviving disk, so you go ahead and invert that matrix, multiply it by both sides, and voila, you've decoded. So that's a standard. This is a standard way to do matrix-based decoding. The arithmetic behind this matrix vector product has to be a special arithmetic. Because you're dealing with W-bit words, you need a closed arithmetic that works on these. When W equals 1, multiplication is AND, addition is exclusive OR, and the world's a happy place. When W is bigger, you've got to use a special kind of arithmetic that works, and that's called Galois field arithmetic, and the notation there is GF2 to the W. So typically on our storage systems, W is going to be some power of 2. Often 8's a really nice convenient value, because when W equals 8, the symbols that you're working on are bytes. Okay? So that's the reason why you want to have W be a power of 2. Now with Galois field arithmetic, addition is equal to the exclusive OR operator, which is nice because addition equals subtraction. Multiplication, however, is more complicated. I'm not going to describe it now, but I'll just say as W gets bigger, multiplication becomes more complex. Multiplying a region by a constant is actually different from doing standard multiplication. I'll talk a little bit more about that. There are a bunch of open source libraries that support Galois field arithmetic, and I'll talk a little bit more about that as well. Okay, so I'll give you my 5-minute state-of-the-art of erasure coding, given that background. The grandfather of all erasure codes is the Reed-Solomon erasure code, which was developed in 1960, so it's an old code. And what it is it's a MDS erasure code that can be defined for any values of n and k. And by MDS, we mean that any m failures can be tolerated. So it decodes as well as it possibly can. Given the definition, the generator matrix that I just talked about, R, the number of symbols per disk is 1. So it just works on one symbol per disk, but it's one W-bit symbol, and W is constrained so that 2 to the W has to be greater than or equal to n. So, for example, if you have W equal 8 and you're working on bytes, your system can be up to 256 disks, which is pretty big. Okay? It has systematic and non-systematic forms. We'll talk about the systematic form only because we're going to store the data in the clear. So with a read-Solomon erasure code, that's what your generator matrix looks like. It just has a big identity matrix, and since we're only dealing with one word per disk or one symbol per disk, each coding disk basically has its own row of the generator matrix. So its general purpose, the conventional wisdom on read-Solomon erasure codes is that they're slow, but we'll revisit that conventional wisdom. But I kind of say nothing fancy because, well, they haven't changed in years and years. A Cauchy read-Solomon code was something that was developed in around 1995, I think. And what it does is it takes a standard read-Solomon erasure code over W-bit symbols, and it converts it into an erasure code that works on 1-bit symbols, but that has R of them per disk, where R equals the original W. Okay? The reason that that is attractive is that it eliminates the Galois field arithmetic, and then all of your coding operations become exclusive ORs, which are fast. However, once you do that, you end up having the density of your matrix plus some patterns of the bits within it affect the number of XORs you do, and they affect performance. Building on that, when storage companies started to have to include something besides single parity RAID in their systems to deal with multiple failures, which was roughly the mid-2000s when the companies started doing this, there's a proliferation of special purpose erasure codes that are not read-Solomon codes that are developed specifically for RAID 6 or 2 failure systems where M equals 2 or n equals k plus 2. And I list them all here. I list about their names. I'm not going to go over what they are, but just putting the names there so you know that they exist. I say the conventional view, and this probably was true back in 2005, is that they're faster than the other codes because exclusive ORs are faster than Galois field arithmetic. And they have far fewer exclusive ORs than the Cauchy reads than if you just turned a read-Solomon code into a bit matrix using Cauchy coding. These are better than that. And there are general extrapolations of even on an RDP coding to larger systems that you can do if you wanted to use the same technology. I'm not going into any of that. I just want you to know that it exists. Okay, and more recently, the most recent research on erasure codes, the big areas are the following. One is the area of regenerating codes. And these are codes whose goal is to reduce the networking bandwidth of rebuilding things when they fail. So they're typically derivatives of read-Solomon codes that do some special purpose work so that when you get a failure, each node does a bunch of computation to reduce the amount of network traffic that's going across the decode. They're very theoretical. They come from the theoretical community, so it means there are a ton of papers, very heavy on theory, and not too much practice to go along with it. But it's a area that has seen a lot of traction. I'll talk about two other codes that have arisen both from companies now. One is called LRC, which is implemented in Microsoft's cloud storage system. And the whole focus on it is improving the performance of recovery from an I/O standpoint while loosening the MDS property. Also, IBM's PMDS codes, plus a derivative of that I've done with the PMDS authors called SD codes, actually address the failure mode of disks failing and individual sectors failing, which is the predominant failure mode in systems right now, so that you can do that, so you can address that failure mode with improved storage overhead. Now, I'm not going to talk about any of that, but that's a bunch of the recent works that's happened. But in general, the research on erasure coding has moved away from CPU and encoding performance and instead worries about recovery, I/O, and network traffic. So not the kind of the guts part of implementing an erasure code. So, on to that, we'll move on to the first project that I talk about, which hits right in that area, and that is improving the recovery performance when you have disk failures. Okay, this is a collaboration that I've had with Randall Borens and his student Osama from Hopkins, with Cheng Huang from Microsoft, and one of my students. And we've had a couple publications come out of it, one in hot storage and one in Usenix. Fast, I put the acceptance rates there not just to brag about how hard it was to get these papers in, but just to show these are the storage conferences are really picky. And so you got to do your work when you want to get something that has a little bit of a theoretical component into the storage conference. Okay, the seeds of this work come from a really weird paper by an author named Zhang. And he presented this interesting property that he discovered on the RDP erasure code. Now, I've drawn here a picture of the RDP erasure code. It's a RAID 6 code, so it tolerates 2 failures. And it has 2 coding drives, which are named P and Q. And it's a multi-row code, so each disk is holding 4 bits. And the P drive, each bit is calculated as the straight parity of all the bits in this row, and that's represented by the gray horizontal lines. Each line represents an equation of exclusive ORs. The Q drive is calculated from these kind of diagonal parity lines that traverse not only the data drives, but also include the parity drives. RDP is a very nice code developed by NetApp. Now, what happens typically when you have one failure in this system, so let's say disk 0, the leftmost disk here, fails. Typically what you do to recover from it is you go ahead and just use the parity drive and calculate the parity of the data in the parity drive, and just like in RAID 5, you do a reconstruction that way. If you use matrix inversion to work on this code, you would actually come up with the exact same way to recover. What Zhang realized was that if you were smart about the bits that you use to recover, and you use some from the P drive and some from the Q drive, that you can use fewer bits to recover. And in this example, you're recovering the data by only reading 12 of the bits rather than 16 of the bits. I'll go back. In this one, you read 16 bits to recover. In this one, you read 12 bits to recover. And why are bits important? Well, each bit is really going to be a giant block on a disk drive, and the main component of overhead in reading it back in recomputing the failed disk drive is going to be actually reading the data rather than performing the coding. So this was kind of a stunning result. And it's a result that a bunch of people saw, and in particular, I think I even have it on this slide, I do. Within 1 week, I was contacted by Randall, who said, I like Zhang's result, and I need to minimize the disk spin-ups for power in my archival storage system. Can we work on this? And then Chang contacted me and said, Microsoft's interested in minimizing the amount of data that we're reading. Now, I want to do this. Well, and me, I just like erasure code, so I said, sure, let's take a look at it. And so the project that we embarked upon with this was, let's take any XOR-based erasure code, which you can represent with a generator matrix that holds bits, and let's try to figure out what the minimum amount of I/O, or the minimum number of bits, are that we need to do to recover from single failures in these erasure codes. I'm going to do this because I don't know if you would die or not. Uh-oh.
Sleeping, right?
Yeah.
Yeah.
Okay. I'm back. Hi.
Still okay.
That's okay. You're good. Oh, I'll get you back right here. There you go. Okay. So, easiest way to talk about this is through an example. And this is an example of a bit matrix code. This is the liberation code. It's a RAID 6 code. And in this example, we have 3 data disks, 2 coding disks, and each disk holds 3 bits. Okay? And that's a generator matrix for it. It's a systematic code, so that the first 9 bits there are all data, and the remaining 6 bits are coding. And the problem that we're going to have here is, suppose disk 1 fails. Okay? Now, the typical thing you would do is, if you're using a matrix-based decoder, is to go ahead and do what I said before: delete some rows of the generator matrix, invert that, and then go ahead and decode. And this is an example matrix that would that would result from that procedure, which is just like reading parity, really, in this example. Well, this doesn't minimize the amount of data read, because if you look at it, every column of this matrix has a 1 bit in it somewhere, which means every piece of remaining data has to be read. However, if you look at the matrix, there are other ways that you can decode. And so, examining this, there are other ways that you can decode each bit. And so what I'm showing here is, I'm going to show you all the different ways that you can decode the first bit on that data drive. And so basically, well, in the first example, if you take the three, if you can see the green lines, those are three bits that haven't failed. That if you take those 3 lines of the generator matrix, add them up, you actually get 1 dot there, which is for the failed drive D1. Good. Okay, that's one way to decode that bit D10. But there's another way. Right? Basically, if you can find any combinations of rows that if you add them up and you're left with that 1 bit, that's a way that you can take some surviving bits and decode from them. So there's an example that takes a whole bunch, takes 6 different bits, but if you take all those bits, rows in the generator matrix, add them up, you're left with the failed bit, etc. Okay, so suppose we've now generated all possible ways to recover each of the failed bits. What we want to do now is we want to choose one equation, or one way of decoding each bit in such a way that the total number of bits in all of those equations is minimized. Okay, now I'm going to formulate this in a different way, because this is basically how you hack it up. Okay, so I'm going to formulate it in this way. What I'm going to do is I'm going to represent a decoding equation by a bit string. Okay, and the bit string basically says, if there's the number of elements in the string are n. It's going to be the number of rows of the generator matrix, which is the number of decoding equation, or it's the number of bits there are. And then if there's a 1 in the bit string, that means, okay, let's add this bit to the equation. If you take all of those bits, which are represented by rows, add them all up, and that equals 0, that's a decoding equation. And that's an equation that can be used to decode any single bit from that string. Okay? So what you do then is, well, I have a couple examples here. These are of equations that you can use that all sum to 0. What you do then is, when you have a failed disk drive, you derive by enumeration all of the equations that could possibly decode that bit. And now, in this example, we have 3 bits that have failed, so these are all the equations that you could use to decode those bits. Now we want to select one string from each of these sets in such a way that the union of them has the minimal number of 1s. So for example, if you take the top equations, you end up with 12 1s, which ends up being all of the bits of the system except for the last 3. However, if you chose the second equation for D11, it's fewer. There are only 10 1s in it, and as it turns out, that's optimal. Okay? So now we have a goal. We're going to enumerate equations, and then we have a goal of trying to figure out which equations minimize the number of bits. Well, it's NP-complete. And I didn't prove it because I'm not a theory guy, but I've got a theory friends, and my theory friend did that in his spare time, because that's what theory people do in their spare time. So it is NP-complete. However, I call it a top coder trick. Top coder is a programming competition, and a lot of top coder problems give you things that are intractable, but it'll give you a graph theory problem that's intractable, but if you solve it by constructing the graph on the fly, it becomes tractable. So we can do something like that, and what I do is I take this problem, turn it into a graph, solve, and make it so that if you can find the shortest path through this graph, you can solve the problem, and then you don't create the entire graph because it's exponential in size. Instead, you only create the graph as you're processing the algorithm. Now, I'm looking at time, and I'm wondering if I'm not going to go through this in detail because there's quite a lot of detail. But I'll give you the basic flavor. The basic flavor of the graph is this. You're going to have a starting node, which is going to be basically It's a 0 starting node. Then all of your nodes are going to be partitioned into levels where each node in a level is going to decode the next bit. So we'll order the bits. And each level is going to contain nodes that decode that bit. And then the edges are going to be from nodes in one level to nodes at the next level, and they're going to represent equations that allow you to decode that bit. And then the weight of that edge is the number of bits you had to read additionally to the ones that you've already read in order to do that decoding, so that the path from the starting node to any node in the last level, the weight of that path is the number of bits that you need to read. So I give an example. It's almost easier to see the example than to describe it. Is I have a starting node, and then what I do is I take the first bit that I decode, and each one of those has an equation that you can use to decode it. So this is how many bits you have to read in order to decode that bit with each equation. Okay? And then if you're running Dijkstra's shortest path algorithm on this, what do? Well, you find the shortest path, and then you go ahead and traverse all the nodes reachable from that path. So the node with there are two nodes with weights of 3. So what we do is we go to that node, and then we create all of the nodes that would come from that. And that's the extra penalty of now using every equation to decode the next bit. How many bits are added when you decode using that equation? And then you would do the next one. And eventually you would come to the shortest path to the end here, which has a total weight of 8. Since you're doing that, you end up not building most of the nodes in this graph. And so that gives you a way of doing this problem. It's still going to blow up exponentially, but it kind of delays the blow up because you're using this greedy algorithm. Okay, so bottom line, we did this, and then we ran it on all the erasure codes we could think of for RAID 6 and the Tolerate 3 failures. And what this graph shows is the savings in number of bits that you read versus the naive strategy of just using the parity drive to decode. The bars have two different colors. The red is only the data, only if the data disk fails. The gray includes the overhead of if the coding disks fail. And what's interesting is you don't just re-encode with the code. If a coding disk fails, you can actually be strategic about it and get some savings by using the other coding disks when you're rebuilding a coding disk. Interestingly, so the RDP result there is that was Zhang's code, which turns out to be good. But interestingly enough, this code called the liberation code, which is a really weird code that I developed through enumeration, ends up having the best performance. Don't know why. I can just say I really don't know why. In terms of the m=3 codes, generalized RDP ends up doing the best of all of them, but the savings are very similar. Okay. As far as actual savings, now I'm going to apologize for this graph because I think it's hideous, and I would never have drawn it, but this came from the student at Johns Hopkins, and I didn't want to redo his graph to keep his self-esteem high. But basically what this graph shows, this is a 12-disk JBOD, just a box of disks. So it's 12 disks at Hopkins where they did recovery. The P drive bars are all the same because they're all doing the same thing. That's the naive strategy. And the optimized bars are using the strategies that we've developed through the shortest path algorithm. And basically what it shows is theory matches practice. The liberation code does have the best bandwidth because it's reading the fewest number of bits. We also have this graph, which I also think is disgusting. I can't believe we published it with those curvy lines. But what this graph shows is that in order to attain these savings, you need your system stripes to have very big blocks. So your blocks, these blocks, the best performance came when my block size was 64 meg, which is huge, right? That's a lot bigger than a sector. However, in today's cloud storage systems, block sizes are about that big because the cloud's got to squeeze the best possible performance out. And basically what these lines are showing is the non-optimized lines are reading from the P drive, and the optimized lines are not reading from the P drive using this strategy, and it's showing that we're getting some performance out of it. In all of this, we ended up developing an erasure code, which I think is pretty cool, so I'm just going to show it to you. rotated Reed-Solomon erasure code. Now here's a different way of looking at Reed-Solomon coding. Rather than looking at it as a generator matrix, we can look at it as a series of equations, and where each equation multiplies some number by the data bits. What a rotated Reed-Solomon code does is it actually adds rows to this, and then for all of the coding disks besides the first one, you end up splitting rows and you encode from different rows. And we call it rotated because if you add 3 to the system, you end up rotating it a little further. This ends up still being an MDS code, but what it gets you is a very interesting property on decoding. When you're decoding from this, you can end up, basically since the rows are rotated, they end up sharing some data. So you can use shared data to decode each of your failed data blocks, and it reduces the amount of data that you need for decoding. Now, I'm not going to go into it beyond that, but it's a very interesting erasure code. Now, I think I'm moving on. Oh, okay, that's good. I can use this slide for it. It's in the slide. We included it in the results. It ends up not being as good as some of the XOR codes, although you'll note for the data in the m=3 case, the rotated Reed-Solomon code does require the smallest amount of data. So it's a very interesting methodology. We developed some theory and some constructions about it, and then we submitted it to DSN, and it got summarily rejected. So the paper is languishing right now on my computer, unpublished. And part of it is that we don't really understand everything completely. I think what is interesting about this work is there is a theoretically open problem, which is what are the lower bounds required on performing recovery on an MDS code? And how can we construct codes that achieve that? It's a very interesting open problem. Love to have anyone help me work on it. Okay, next. I had planned this for an hour. I assume we're good. Is that okay for you? Okay, good. Next is the project I called Screaming Fast Galois Field Arithmetic. This is a collaboration with Kevin Green and Ethan Miller. Ethan's at Santa Cruz. Kevin's at Data Domain. Kevin was Ethan's PhD student. And this is a result that we're presenting in FAST this year in February. We're also planning on having an open source library that has all of this ready to use, documented and out by FAST, and we'll have the GF Complete journal paper submitted in April, which is going to be the grandfather of, or the mother of all Galois Field Arithmetic implementation papers. So a lot of work going into this. Now, to motivate this work, let's return to a Reed-Solomon erasure code. So Reed-Solomon erasure code, every coding disk is the linear combination of the data disks in the Galois field. So let's map this to a strike. Okay, so down on the bottom is the block view of a strike, where you have a big block that's decomposed into single bytes, and each byte is kind of in its own separate encoding equation. So what this looks like when you're implementing it is, and this is, let's say we're encoding the very first row of this, so we're talking about how to encode C0. What we're doing is we're taking each coefficient from the generator matrix and multiplying it by a block, where each block is broken up into words, so we're doing multiplication of each individual word on the block, but really we're multiplying the whole block by a constant. So the important operation becomes multiplying a region of bytes by a constant in a Galois field. Okay? Now the conventional wisdom on this is that multiplying a buffer of bytes by a constant is equal to, if I have n bytes there and I'm multiplying it, it's equal to n single multiplications. And in a result that I had published in 2009 that did a performance evaluation, it showed that in GF2 to the 8th, multiplying a region by a constant was roughly 4 times slower than doing an XOR. And that was on a 32-bit machine, and it kind of makes sense because for each 32-bit region you have to do 4 table lookups to get the 8 bytes out. Okay? This is one of the reasons why we have the big proliferation of XOR-based erasure codes, because XOR is so much faster than Galois field arithmetic. However, you go to conferences like FAST, and I kept kind of hearing these eerily smug reports from industry that they can do Reed-Solomon coding at cache line speeds and don't need XOR-based erasure codes. And I would say, can you tell me how this is done? And they would say, no. because I'm a company and I want to make money. So no one gives you the secret handshake on how to do this. Well, I got the handshake. I procured the handshake, and I would like to say I procured it from Ethan, who's a co-author. He's the one who showed me the handshake, so I'm going to show you the handshake. Now, showing you the handshake doesn't require any knowledge of Galois field arithmetic other than addition equals exclusive OR. The cool part about this work is that different values of W require some different techniques, and in particular, W equals 16 and 32. If you represent your words in memory in a different manner, you end up really being able to speed stuff up. Again, this is going to be released as open source in the next month. Now, it's based on Intel's streaming instructions. So, as I like to tell my class, Moore's law is dead. And one of the artifacts of Moore's law being dead is our computers, our processors have now become junked up so that we do more rather than doing less fast. We do more at the same speed. And one of the things that we do more now is we can work on larger regions of memory. And in particular, Intel has support for working on 128-bit regions of memory. And these operations are ubiquitous. They're on basically almost all machines that we buy these days have these instructions on them. So they work on 128-bit vectors. I give an example. A very easy one is set EPI 8. Basically, when you have 128 bits, that equals 16 bytes. And so that instruction, you give it a byte, and it replicates it 16 times. Obviously, you're going to have some arithmetic. There's bitwise and bitwise exclusive OR. Those are important ones. There's left shift here. The example on the bottom, that's the left shift instruction, which you give it X, and it's going to do two 64-bit left shifts by X. So in the picture, I choose X equal to 8. So basically, it's moving everything 1 byte over to the left, because that's 8 bits. And since it's a 64-bit instruction, there are 2 zeros that get put in. Now, the killer instruction in all of this is shuffle EPI 8. This is a cool instruction. What it does is it takes 2 vectors of bytes, so they're 2 16-byte regions. The first one it treats as a table, a table of 16 bytes. The second one, it takes every byte of the 16, and it only looks at the bottom 4 bits, and it uses those as an index into the table, and then it performs 16 simultaneous table lookups from that table into a resulting 128-bit vector. And so the examples I give here, you see B on the top, and if you look at the leftmost one, it says C. So there in the target vector, it goes ahead and it took the Cth byte, which was 5A from A, and went and put it into that index's slot in the target vector. And you can also see there those 4 middle bytes. They all say 0A, so that byte AB, which is at position A, gets put into all those target locations. So the key is 16 simultaneous table lookups, all in one instruction. So it shouldn't be too hard to envision how to do that if you're doing table lookups. So what you do with Galois field arithmetic, and the example I'll give here is in GF2 to the 4th. In GF2 to the 4th, you have 16 possible values that you can have because you have 4 bits. So if you're doing multiplication, in this example I'm saying I'm going to do multiplication by 7, I can take all of the values of multiplying 7 by anything and put them into a 16-element table, and that's up top. Okay, and I have it backwards because it makes more sense when you're looking at it that way. So 0's on the right, and I label all the bytes in hex. Okay, so I have that table, and you'll also notice 7 times 0 does equal 0, and 7 times 1 equals 7, so the math isn't too hard. I make another table just by bit shifting that 4 bits to the left. So you can see the second table is the first table, but it's just bit shifted. And I got a couple masks in there that let me strip off some bits. And what I'm going to show you is multiplying this 128-bit vector A, which is going to be decomposed into 32 4-bit words. So each 4-bit word is one digit of hex. Okay? So I'm going to show you how you multiply this using the SSE instructions. Okay, so we set up the tables and masks, and just to show you, right, the first 4-bit word is 3. 3 multiplied by 7 equals 9. It's right there in the table. So the first bit of our target vector should be, or first word should be, or first 4 bits, sorry, should be a 9, and the second 4 bits should be an A. So our product should definitely start with 9 and A. That won't prove that it's correct, but that'll give us a little bit of a measure of, okay, maybe it is. So the first thing you do is you use the mask to to mask out the high bits so that you're only left with the bottom 4 bits of each byte. Okay? Then you use those as indices into the table and do your 16 simultaneous table lookups. So boom, 16 multiplications done. Right? Then you go ahead and you mask off the high bits, shift them over 4 bits to the right. Now you use them as indices into the table, do the table lookup. So now you've done the other 16 multiplications and XOR them together, or you could just even OR them together, and you get the result. And you'll note the 9a is there, so we have some measure that it's right. So the cool thing is 6 instructions to do 32 multiplications. That's pretty cool. Okay? When you move to GF2 to the 8th, you use something we learned in elementary school, but that we forgot because it didn't have any real meaning to us. But the distributed law of multiplication says that I can break up a word, an 8-bit word, into 2 4-bit components, and then I can do those 2 4-bit multiplications and add them together, right? And that's what that equation says. And when I'm doing arithmetic, it's equal exclusive or, so you exclusive or them together. So what all that really means is you have 2 16-byte tables for table lookup, one on the low 4 bits and one on the high 4 bits. And I have them there, and unlike before where in GF2 to the 4th, every table entry started with a 0, here your table entry is, right, we're doing arithmetic over bytes, so the tables are going to have bytes in them. But otherwise the code is identical at GF2 to the 4th, same 6 instructions. Works very nicely. Now for 2 to the 16th, we use table lookup again, and we use the same distributive law, but now we're going to have 4 4-bit regions for every 16 bits. Okay? Now the problem with this is that MMI shuffle EPI8 gives you bytes. It doesn't give you shorts, or it doesn't give you 16-bit quantities. So what you have to do then is you have to split up each product into 2 separate tables. One table for the high byte and one table for the low byte. So we got 8 tables. 4 ways of splitting up the word each product is split into 2. Okay? Now, when you go to implement this, you realize that it's a little bit cumbersome. And I'm going to show this because it leads to representing your words differently so that it works faster. If you map your 128-bit vector into 16-bit words, like I have in this picture, okay, and I have each byte is a rectangle, every 4 bits is represented by a letter. You're going to have to do 8 table lookups for the 8 products, and I show each table lookup, right, you're going to have the low byte, you're going to have the index in the low byte, and you're going to have to ignore the high byte when you do the table lookup, and then you got to shift it over and look up the high byte. So you're going to look up the low byte, the high byte, the low byte, the high byte. You're going to do your 8 table lookups, but every time you do a table lookup, you're going to have 8 of those indices be empty because you can only do the low bytes and the high bytes. Now instead, you can take 228-bit vectors and take your 16-bit word and split it among both vectors so that one vector has all the high bytes, one vector has all the low bytes. So you'll note, in the left vector, all the subscripts are 3 and 2 because those are all the high bytes, and on the right one, they're all the low bytes. Now you still have 8 table lookups when you're going to do your arithmetic. However, if you do all the low bytes together and all the high bytes together, you don't have to have 0 indices anywhere, and you end up doing all 256 bits worth of multiplication in the same 8 table lookups. So by splitting memory, I call this an alternate mapping, by splitting your words over 2 memory regions, you're able to make use of that shuffle operation much more efficiently. Okay, I call this the alternate mapping. I say it has all the properties you need because although you're mapping your words differently, it doesn't matter. As long as the arithmetic's sound, you don't care how you represent your words in memory. So it's not like you need to convert memory to this alternate mapping. You just need to treat your memory as having split words. It's a little confusing, and it's harder to read memory. It's harder to debug your code for sure. And you can convert the standard mapping back to it with 9 instructions if you want. Now in GF2 to the 32, Same thing, only now it's really disgusting because now each 32-bit word is 8 4-bit words. Each product is 4 bytes, so you got to have 32 tables to do your table lookup. It's the same alternate mapping technique, only now instead of having 2 vectors, you're going to have 4 vectors, and each word is split over 4 vectors, so it's even harder to read. But you can still do everything that way. Now, we've hacked it up. Check out the performance, and this is a pretty meaty graph that I've got. And part of the reason it's meaty is because the paper is 6 pages, so you only have so much room to put stuff. So this is all the information. Now, what it is I've got a Linux box. It's a 3.2 gigahertz Intel Core i7, which is a pretty recent processor. It's got a 256K level 2 cache and 8 meg level 3 cache. And what I'm doing is I'm doing buffer constant multiplication on various buffer sizes, ranging from buffers which are 1K in size to buffers which are 1 gig in size. So those x-axes are log axes. Okay? The y-axes are also log axes. Okay? And what I'm showing is on the top set of curves are, I call it SIMD. Those are the techniques that I've just shown you. All of the other, and I also on the 16 and 32, I split out using the standard mapping and using the alternate mapping, and using the alternate mapping is indeed faster. All of the other lines are different ways that have been conventionally used to implement Galois field arithmetic, and actually some of them aren't very heavily used, and they should be, particularly those yellow lines. So the green lines on the low 2 are just standard using a multiplication table, which is typically what ends up happening. However, you can be smart about your multiplication table. Instead of, for example, when w equals 4, rather than doing individual table lookups on a 16 by 16 table, you can actually lump them together so that you're doing 16 bits worth of table lookup at once on a much bigger table, and that's why the yellow line's faster than the green line. However, once the field size gets bigger, you have to construct that table on the fly, because you can't hold it in memory, and that's why the yellow lines kind of start from the bottom and go up, is because you have to construct the table when you do the multiplication, so the larger regions amortize that. When w gets bigger, for w equals 16, you use discrete logarithms to implement Galois field arithmetic. That's the red line. And when w equals 32, the best performing technique is actually to split each word into 4 components, and you end up doing 16 submultiplications using 7 different tables to do the multiplication, and that's there in the purple line. Now, on the right side, I've got baselines to compare this to, and that is I've got the speed of memcopy, just copying bytes from one place to another. I've got the speed of doing XOR using the SIMD instructions. And then I also have what I call Anvin by 2. Peter Anvin documented a way where you can multiply a region by 2 in a Galois field, where you can lump them together. You can do it 128 bits at a time, and it's real fast. And basically what these curves show is that the speed of performing the arithmetic is roughly equivalent to doing Anvin. It's almost roughly equivalent to XOR, and basically it's cache limited. Right? Until you use up your level 2 cache, you're getting a certain amount of performance. Then once the level 2 cache gets filled up, you get a big drop in performance, which means that your operations are no longer CPU limited, they're cache limited. So when someone says, I can do Galois field arithmetic at cache line speeds, that's what they mean, is that you're getting that. So basically what we're showing is cache line speeds. And the improvements in performance is a factor of 2.7 to 12 times faster than other things. Factor. Usually people are happy with 10%. This is a factor of 12. So it's a dramatic increase in performance. Now, I implemented this again. It's part of the library which I call GF Complete, because GF Complete implements that and every other known technique that you could possibly use to do Galois field arithmetic. And that'll be released by FAST. It'll be documented in a journal paper. That's out. Now, I call this a game changer because of the factor of improvement. When you can do Galois field arithmetic as fast as you can do an exclusive OR, all of a sudden you're no longer restricted to XOR-based codes, and your code design becomes you can worry about other properties. And so recent codes for doing various things in terms of erasure coding, all of the ones that I'm showing you here are all codes that are based on Galois field arithmetic that really 6 years ago you couldn't sell these codes because everyone says Galois field arithmetic's too slow. Now that you can do it fast, you can start designing other codes. So it's a liberator in some respects that you can actually start doing more flexible design. Okay, so conclusions of my talk is that erasure codes are everywhere, and there are a whole bunch of different dimensions that people worry about with codes. And it's not just CPU performance, and it's not just XORs. And there are lots of interesting open problems and theoretically open problems that have arisen that actually matter in erasure-coded storage systems. I'm working on a bunch of these. I like theory, but I also like practice. One of the things I also want you to get out of this is that I do have a bunch of open source libraries that are all there to help with erasure code. So obviously I've talked about GF Complete. My JErasure library has been around since 2008. It uses the old version of Galois field arithmetic, so it has a bunch of the XOR codes. My whole goal for this summer is to get JErasure up to speed with everything else, plus add some more erasure codes that have come around since 2008, have that out as open source. I have some other stuff that's also there as open source, so if you're interested in erasure coding, just go to my webpage and you've got a lot of tools at your disposal. Okay. That is the end of my talk. Thank you.
Thank you very much.